All righty. Welcome back, everyone. Ralph, you want to introduce Fran to everybody?
Certainly. So it's hard to put all of this into short words, but nevertheless, let me say a few words about Fran. Fran, of course, grew up in England, degrees from the University of Lancaster in England, and then coming to the U.S. PhD at MIT, which is where she and I met each other back in the 1970s. She's currently the assistant director for planetary science at the Laboratory for Space and Atmospheric Physics at the University of Colorado at Boulder. She's been at Boulder for quite a few years now. And I'm going to go ahead and cut to the chase and just say that she's, of course, been working as a co-I on New Horizons and was part of the Pluto underground from the very beginning. Also worked on Voyager, Galileo, and Deep Space One and Juno. So she's going to tell us a little bit about New Horizons exploration of the outer heliosphere and how that feeds into what we're currently learning about the outer heliosphere in our astrosphere that we've been talking about today. Fran, over to you.
Thank you so much, Ralph. Excellent. And I want to tell you about not the main target of what New Horizons has been up to, which is, of course, going past Pluto and Arrokoth, and hopefully, with a bit of luck, maybe another object in the Kuiper Belt, another Kuiper Belt object. But I want to talk about exploration of the outer heliosphere, because I think this complements most what people are interested in with respect to Interstellar Probe. So if we can go to the next slide, please. We have had so few missions exploring the outer heliosphere. New Horizons is that, if you look at the far left diagram, is the orangey one that is now actually out more like 50 AU and is going the same direction as Voyager 2, but is in fact going in the ecliptic rather than south ecliptic like Voyager 2. So you can see very limited number of missions have been out into the outer heliosphere, and we hope to make some observations between Voyager and the Interstellar Probe. Note that it's also heading out into the direction of the energetic neutral atom ribbon, and so will complement observations made by IBEX and IMAP. Next, let me tell you a bit about New Horizons spacecraft. And this is a really small spacecraft. It's the size of a piano, a baby grand piano, if you like. And the antenna is about 6 feet across. So it's relatively small. It does have an RTG, powered by an RTG. The instruments here, Laurie and Ralph are both cameras. Unless we find another target, they're not going to have things to look at. But the Alice UV instrument will be looking, ultraviolet spectrometer, can map the sky. We'll talk about those. The student dust counter can count dust, that is particles, great sort of micron-sized particles. And then SWAP PEPSI, our particle instrument. SWAP measures the solar wind, PEPSI energetic particles. And then REX is the use of the radio antenna to do science. And there's probably not a lot of science to be done in the outer heliosphere with REX. So let's move on to the next slide. Tells you the status of the spacecraft. It seems to be doing well. It's healthy and doing well, but we've currently been through one extended mission, and we're about to apply for the next extended mission, which will be fiscal year 23 and 25, and that will take us from 55 to 65 AU. But there's good reason to believe that the spacecraft can continue through the mid to late 2030s. And I'll show you in a bit where that takes us. Next, please. And indeed, if we look at the power, you can see here that the current power is about 182 watts and is heading out. We'll get to 82, we'll be at 150, and 100 AU will be at 130. So Power is probably okay to keep going out past the termination shock, maybe further, and we'll see how we do with other resources. Next. So what we've been up to is obviously after a flyby of Jupiter to get a gravity assist out to Pluto, observations of Pluto, but then beyond Pluto, observations of MU69, 2014 MU69, which is later called Arrokoth, this small object, cold classical Kuiper object in 2019, and then making observations of various objects at different phase angles in the outer solar system. But of course, what we're really interested in is, we, being those of us who are interested in heliospheric science, is the plasma, the dust, and the neutral gas that's out in the outer heliosphere. Next. So I'm going to, what we've done so far, I'm going to talk a little bit about what we've been doing so far in the outer heliosphere in this respect. Solar wind and pickup ions are the most important, of course. Measuring the dust density, which is getting some very interesting results, and then mapping out the Lyman alpha, which tells us about the distribution of hydrogen. And we hope with the next extended mission to continue these and go further. Next. So this is what we're going to do. I'm going to go through these different measurements and tell you what we expect to see. Next. So let's start with the dust counter, called the Venetia Burney student dust counter, after the young girl who in the 1930 named Pluto. And so it seemed appropriate for a student instrument to have her name on the instrument. This was originally sort of designed as an education public outreach instrument, but has been doing a fantastic amount of work built and operated by students. And we're now at the 7th generation of students working on the SC. And it's been making measurements of micron sized particles. And it's the only observations beyond 18 AU. So the next slide shows you the results. So the dots are the observations, the flux of greater than 0.63 micron dust particles. And you can see that it's sort of fairly flat in the outer heliosphere, but there are some upswings and downswings. Now, if we look at models, so these are models that take the distribution of objects that are believed to be out there and calculate that if they bump into each other, they generate some dust at some rate. And there's big debates about the drop-off in the distribution of Kuiper belt objects in the outer heliosphere. And so the big question is, does the Kuiper belt extend much further than 50 AU, or does it suddenly disappear? And that is a current big issue of debate right now in planetary science. But from a dust viewpoint, we have some big questions, and this is a log scale. So we're talking orders of magnitude difference. And so measurements by New Horizons beyond 50 AU are going to be key in sorting out this question. Next. Let's move on to the UV. The FUV spectrograph called ALICE is able to scan the sky and has done so far 6 great circles, and will continue to make these mapping out of the distribution. And this is obviously important for the interplanetary medium to try and work out what the interstellar medium is, as well as the interplanetary medium. And so just mapping the sky is one thing, but if you go to the next slide, I'll show you this ingenious idea that if we have New Horizons looking out, and then you have an instrument, say at Mars, so the MAVEN IUVS, that is based here in CU, can look out from Mars, out at the interstellar medium, and then you do the same maybe with LRO instrument at the moon, and then you compare the difference between what New Horizons sees with what something, a UV instrument in the inner heliosphere sees. That difference gives you the amount of hydrogen, the column density between the two spacecraft. So this is a really key measurement that will tell us about the distribution of hydrogen that's in the outer heliosphere, how much is really coming in and from the outside and penetrating in to the heliosphere, and how far it gets before it becomes ionized. And so this will be a very useful measurement that can be made by the New Horizons ALICE instrument. Next, we move on to the particle instruments, and these are the only measurements right now that we're making beyond Mars. Okay, so Juno is well inside the magnetosphere and will not go outside at Jupiter. And so all we have are measurements at Mars, say MAVEN instruments, for example. And then we have the Voyagers that are out in the interstellar medium. So New Horizons making measurements of the solar wind using the SWAP instrument. It has a capability that Voyager did not have, the Voyager PLS instrument, which is the one that Ralph and I worked on as students at the planets. That is not able to measure the pickup ions, doesn't have the energy coverage. And so there are key measurements that are being made by the SWAP instruments here in the outer heliosphere, and should, with a bit of luck, make it to the termination shock and make high resolution measurements in the out there as it crosses. Next. Some of the important observations that have been reported by Heather Elliott in particular with the SWAP instrument is to look at the evolution in the structure of the solar wind. And the primary cause of this is a combination of, first of all, slowing down of the solar wind due to the slowing down of the solar wind due to the ionization, the mass loading that's produced by the ionization of neutral material. So the neutral material that the ALICE instrument detects that hydrogen coming in becomes ionized and then picked up into the solar wind, slowing down the solar wind. And we can see this in the observations made by SWAP. And so this is a key measurement of the pickup ions, the mass loading by the pickup ions. But then also these pickup ions cause the heating of the plasma in the solar wind. So these evolution has been observed largely for the first time by the SWAP instrument. And furthermore, the changes in the structure that are observed, if you go to the next slide, you can see that as the solar wind moves out in the outer heliosphere, the small scale structures are worn down. They merge together to make larger scale structures. And so the periodicity becomes longer, and there are sort of larger swings in structure rather than small scale variations. And this has really been observed in detail by the SWAP instrument on New Horizons. And we'll continue to see how this evolves as we move beyond 50 AU. We move to the next. We have here the PEPSI instrument. So the PEPSI instrument, SWAP covered 35 EV to 7.5 keV, where the PEPSI instrument covers, get the numbers in front of me, 25 keV. So it overlaps, sorry, doesn't quite overlap. It extends above the SWAP energy up to MeV ranges. And what we can do here is then measure, most importantly, the pickup ions. And so PEPSI has been the first instrument to measure these helium pickup ions. SWAP tends to measure the hydrogen pickup ions. But both instruments are getting this tail. And this really nice plot on the right shows you the extended high energy tail, the superthermal tail, key for the energetics, understanding the flow of energy in the solar wind in the outer heliosphere. And so it's able to measure the solar wind, the higher energy component of the solar wind, as well as cosmic rays as we move out into the outer heliosphere. Okay, next slide. So the New Horizons papers, many of these are published by Matt Hill, shows this structure, the modulation of the galactic cosmic rays that has been observed before, associated with solar activity. But important here is that the Voyager era was a different era, even though it was key in making these measurements. And so we're going to have at a different epoch the measurements made by New Horizons, and then again a different epoch measured by the Interstellar Probe. So those three measurements will be key for understanding how things are varying out in the outer heliosphere. And I have to point out that, you know, understanding of the inner heliosphere, the material, solar wind in around the Earth and out to Mars and maybe Jupiter, has taken many, many spacecraft to really understand it and put the picture together. And here we are, we will have three, and hopefully that will help us understand what's going out here. So those who say, well, Voyager, hasn't Voyager done it all before? I know I'm preaching to the choir here, but of course, just getting a single another pass through with rather different instrumentation makes a big difference in these measurements. Okay, so let's go to the next slide. Of course, if you only have a limited number of passes through any environment, you need to put the measurements together with models that, and you use the data to constrain the models. And in particular, the pickup ions and understanding the role of pickup ions in slowing down the solar wind, in heating the environment, and watching that evolution as it goes out will be key. But also putting that together with the measurements by Alice of the distribution of neutral hydrogen, which of course is the ultimate source of the material that gets ionized to form the pickup ions, will tell us a lot about the energy, the evolution of the energy in the outer solar system. Let's move to the next slide. In particular, the New Horizons team has been working with Merav Ofer and her team and trying to provide constraints on for the models that are really trying to understand the influence of these pickup ions, the global structure of the heliosphere, how the energetic neutral atoms are generated and their distribution, and then the structure of the shock. What is the actual structure? And New Horizons, once it reaches the shock, will be able to make some very important contributions there. Next slide. I know that Merav is going to be talking, I believe tomorrow, she'll be talking more about her modeling scheme, but she has a program that is trying to understand the structure of the outer heliosphere, and we will be able to provide constraints from New Horizons Chem 2. So if we go to the next slide, we hope to have the synergies between a whole variety of different observations, past observations such as Voyager and IBEX, but future measurements of the ENAs by IMAP, but also working with UV instruments that are in orbit around Mars and around LRO around the moon to make these measurements together to pin down things like the neutral distribution in the throughout the outer heliosphere. Next, so the big question is, will or when will New Horizons reach the termination shock? And here's an estimate that produces indeed quite a wide range because, of course, it depends on what's happening with the sun as to where the shock actually is. There's a wide range here from 4 to 16 years, depending on whether the shock is at 62 AU or 95 AU. Pick your number, but it'll be very important to have the measurements that New Horizons will make as it makes that crossing. And so I will wrap up with the next slide. I have just a synthesis here, a list of the instruments, the science observations, the collaborations, and what we hope to measure. And I'll end with the last slide so we can have a little time for questions, summarizing what we hope to do. And, you know, I'm going to go straight to the questions, see if what people want to ask. Who's going to read the questions? Is that you, Ralph?
I can certainly read the questions for you, or Ralph can.
I'll let Andrea do it.
Okay. Thanks very much for your patience, Fran. So Bernd Heber asks, what about measuring above 10 MeV to GeV electrons as measured by Ulysses on its way out to the heliosphere?
Okay, that's a question for either Ralph or Matt. Ralph, do you want to take?
So this is on. I'm assuming. I'm sorry. I'm assuming this is on New Horizons. So right now we've got with respect to New Horizons, the galactic cosmic ray data we're getting are actually the background measurements that we're seeing in the electron detectors that were put on for Jupiter. So being able to actually see electrons at those kinds of energies, we just really do not have the kind of geometric factors and the kind of sensitivity to be able to make those measurements. It just wasn't in the original specs because it wasn't there for one of the main science objectives when we were putting the mission together.
So, and I also see a response from Matt Hill that says we can't measure such electrons with PEPSI.
Matt put it much more succinctly than I did.
Thank you, Matt.
So we also have a question from Marshall Eubanks. Isn't New Horizons being used to acquire distant, as in 1 pixel, images of TNOs, that is, TNOs fairly far from New Horizons? And doesn't that mean the use of LORRI will continue even without another close flyby target?
You know, we're trying to decide what to do for the second extended mission proposal and what our strategies are. So do we use fuel to turn the spacecraft around to look at things, or do we just use ground-based assets, like Earth-based assets like Hubble, to look for more distant targets? So that question's up in the air right now.
A question from Conzello Barnhill. Will there be any aggregation with data from the solar probes and the outer heliosphere probes to create a more accurate model of the topological structure of the heliosphere and its change over time?
That is exactly what Marav Ofer is working on, and I think she's giving a talk tomorrow on exactly this topic.
Oh, perfect. And just checking she's going to be speaking tomorrow at 1:30 p.m. Eastern time. So thank you. In terms of, and Marav just said yes, so thank you, Marav. And I think that actually takes us, we might have one more question here. Suggest previous, this is from John Cooper, I apologize. Suggest previous talk defined inner heliosphere as out to 70 AU, not the way we usually define it, heliophysics, inwards of giant planets to the sun, needs some commonality of terminology here.
Yes, it's like energetic particles are relative, right? What's energetic versus low energy, right? It's the same with inner heliosphere and outer heliosphere. It's somewhat relative. Yeah, we could come up with a definition or just talk about distances.
Okay. So with that, we actually look like we are now at 2:30 p.m. So Fran, thank you so much for an excellent talk. And thank you. What we will do now is we will transition to, first of all, we have a break for 15 minutes, and then we have a very special student program. It's also applicable for early career professionals that will be taking place in a separate Zoom room. I will put the link for that Zoom room in the chat if people are interested in just going there now and waiting while we get ready to start. In the meantime, please everybody enjoy your break, and do consider joining us for the student and early career program that will be taking place in 15 minutes at 2:45.